Hello, Mr. Sorrentino here again, bringing you another one of these lecture videos for Math 31. And this one deals with rational functions. Now, up to this point, we've worked with rational equations and learned how to solve them. And one of the things that we always look to with those is that there was always complications involving domain restrictions. Um, and we're going to see how that domain restriction gets handled here. We're also going to talk about these functions a little bit more detail because oftentimes when there's domain restrictions, there's also range restrictions as well. And we're going to talk about those as well. Um, in the process of dealing with these, we're going to do some factoring techniques and other such things, and even some division and things we've done in the past when we were dealing with polynomial functions. Because if you remember, if you go back to when we were solving rational equations, we would often cross multiply and end up with quadratic equations, and that could also um, create, if you have more complicated rational functions, you could end up with cubic equations and so forth as well. And we avoided them at the time when we were dealing with rational equations because we hadn't learned about polynomial equations yet. But now that we've talked about and worked with polynomial equations in this chapter, we can now handle those as well and use techniques for those. So we're going to talk about rational functions here, and in particular in this section, we're going to learn how to create their graphs again accurately without hopefully having to plot a whole lot of points and making a table up just to have only a part of the graph. And that's one of the things again that we're always concerned with graphing, especially if you're trying to come up with a relative idea of what the graph looks like yourself. Even if you have a graphing calculator, you end up might having just a partial picture of it depending on where specific things occur with the graph. And if you're not if your window isn't zoomed on that, or if you're graphing it by hand and you're not choosing the right values of x to put into your function, you may not see the entire picture and end up thinking that the entire graph is something that it really isn't. So we want to kind of be able to take these things into consideration so that we know certain things to look for in these graphs, so that if we're not seeing it on a graphing calculator or any other kind of graphing program on a computer, or if you're drawing it yourself and you're not seeing some of those features seem to be coming about in your graph, then um, that kind of gives you an indication that you may need to explore other parts and try other numbers and see what happens. So a rational function is made up basically of the division of two polynomial functions, and that's what its official definition is. It's basically we have the division of two functions where those two functions are polynomial functions. So that's all they are. They're the division of two polynomial functions. Now, when we have a polynomial function in the denominator, which means we probably have at least one variable of x in there, it may be appearing multiple times, raised to different powers and things like that. As soon as we get x's in the denominator, we run into a potential to have a situation where q of x would equal 0. But the thing is, that is something we don't want, because that means for that particular value of x, this new function that's the result of dividing these two other functions doesn't exist. So what we have to be keeping in mind is that we do have domain restrictions of rational functions. It's any value of x where q or 0 is where x is a 0 of q of x. So again, we don't want this to happen. We want q of x to not equal 0. Well, these domain restrictions, which we can identify. I mean, if we factor, in these cases here, you're not going to have some situations like we did in the first four sections here, where the factors may or may not be as obvious. They're going to be obvious pretty much all the time. So you should be able to factor um, the functions that make up the rational functions pretty easily. I mean, although there are instances where there's functions that the domain that the numerator and denominator may not be all that factorable, you're not going to be asked to consider those for the most part and for the span of this course. You may see them in other courses and have to keep aware that you might have to try to figure out ways of finding them out, but you know but domain restrictions, any of these places where where the bottom function becomes 0, which makes the whole function undefined, they come out to be two different things. There's two different phenomenon that happened with these kind of graphs of rational functions that it happened because of domain restrictions. I can either have what is known as a vertical asymptote, or I can have a hole. Just for a side note, in calculus, they may refer to these as a vertical asymptote would be an infinite discontinuity, and the hole is sometimes referred to as a removable discontinuity. The reason it's important to kind of note this, more so for the hole, is because its name, removable discontinuity, kind of lets us know whether or not we have a hole or not, because a removable discontinuity implies that we have a cancellation. We have a cancellation that's possible that would simplify the function. Now, when I simplify, and although the cancellation can happen, which makes it easier to graph, easier to calculate things, I have to keep in mind, though, that the cancellation does not mean that we forget about the domain restriction. It just means that we have to account for it as being a hole. So let's see how we could identify what these are. So let's have a look at example 1. And example 1, 2, and 3 are basically the same 4 functions. We're just looking for different parts of them. And to eventually, in example 3, we could write a graph of the function. So that's what we're looking to do here. So in example 1, we're just going to try to identify any vertical asymptotes or holes in it. So let's have a look at example 1 and start this process. So for these first 2 functions, looking at A first, it's a pretty simplistic function here. I can say by looking at it, well, obviously x cannot equal a -4, because that would cause there to be a 0 in the denominator. This is a domain restriction. Now, is this a vertical asymptote or a hole? Well, how I make the decision is, okay, I look at this and say, well, is there any way for that, the thing that causes this domain restriction is me having this x plus 4 in the denominator. Is there any way for me to cancel out this x plus 4? Is there anything on top that I can cancel it with? I just have a number 2 up there, so no. There's no cancellation possible. And since there's no cancellation possible, x equals -4 is a vertical asymptote. That means whenever I eventually do a graph, I'm just going to do a really quick rendition of one right here. Here's my graphing region. And say here's -4. I'll usually will indicate that by putting some sort of vertical line in there to indicate that that's a vertical line that the graph can approach infinitely but never cross. In vertical asymptotes, they can never cross. So we talk about horizontal and oblique asymptotes as we move on to this. That's a different story. So let's look at g of x. G of x, now whether I factor the bottom or not, I could probably figure out what values of x would make the bottom 0. But just for the sake of argument, and this also helps for the discussion we're doing here, I can factor the bottom into x plus 3, x minus 3. And I'm just going to put a parenthesis up here as well. So my domain restrictions are that x cannot equal -3, because that's going to create a 0 with that one, and x is not equal to 3, because that'll make this one a 0. So I have 2 domain restrictions here. But what kind of domain restrictions are these? Well, if I look at the function that I have in front of me, once in the factored form, I can see that the top has an x plus 3 being multiplied essentially to 1, and I have an x plus 3 on the bottom being multiplied to x minus 3. That means that I can cause a cancellation. That cancellation means that g of x is approximately equal to 1 over x minus 3. And if you would graph x plus 3 over x squared minus 9 and 1 over x minus 3, you would see on a calculator or a computer, you would see exactly the same thing. The reason being that there is a difference between them because of the fact that, this function here has no issue with x equaling negative 3. In that purple version of g of x equals negative 3 is perfectly allowable. The problem is it's not allowable in the original function. So so there would be a hole here, and that's basically what caused here the x plus 3 would cause the issue with the negative 3 being an issue, a domain restriction, has been removed. Hence the name removable discontinuity. Therefore, I can say I have a hole. Now, a hole is going to be a set of coordinates. I can't just say I have a hole at x equals negative 3. I know that negative 3 is going to be the x value because x cannot be negative 3. Now, the y value I would get by, go to a different color here. Let's see, I'll use that purple. To figure out the y coordinate that goes here, I'm going to just simply do g of negative 3 on the purple version. And I do 1 over negative 3 minus 3, which ends up being a negative 1/6. And so I have the location of the hole. Whereas, since the x equals 3 is still an issue in the simplified form, I'll say this is just a simplified form, it's still an issue in there. That indicates that is a vertical asymptote. So I have a vertical asymptote equals positive 3. And that's how I make the determination. A cancellation, once I determine what are my domain restrictions, if the cancellation eliminates one of those domain restrictions, that becomes a hole. If once I cancel, if there is no cancellation I can do, once I simplify the expression, if it is able to be simplified, and once I simplify, the domain restriction I noted before is still a problem, then it is going to be a vertical asymptote. So this one would have a hole and a vertical asymptote. And we'll show later how to graph them and deal with those when we get to the point of graphing them. On to C. So for this one, let's have you do a little work here. In C, what are the domain restrictions for C? Well, as before, for me to find domain restrictions, it's usually a good idea for me to factor the top and bottom. Now these are going to be factorable. You may want to go and use the AC method. I'm not going to show the entire AC method here for the sake of time for this, but the top would factor into 4x, this would be x, this would be a 4 minus and a plus 1. So 4x plus 1 and x minus 4. Down here, the bottom would factor into 2x minus 3 and x minus 4. So with this in mind, I could easily identify what the domain restrictions are. X cannot equal 3/2 or 1.5 because that's going to create an issue in the first one. And x cannot equal 4 because that's going to cause an issue in the second quantity I have in the denominator. Well, when I look at these functions, I can note that h of x, let's go to a smaller one, it's a little thick there. H of x can be rewritten or simplified, and I'll just say it's a simplified version, The x minus 4's would cancel. I had the 4x plus 1 and the 2x minus 3. So the fact that the x minus 4 is canceled, and those are the issues that caused me to have x equaling 4 as a domain restriction to begin with, that indicates that I have a hole where that x equals 4. Of course, I had to do a side problem down here. I gotta say, okay, well, what's h of 4? And I could do that in the simplified version, because, if I try to put it in the original version, obviously I'm going to get 0 over 0, which is not anything. And we're not going to get into that a whole lot. Once you get into the pre-calculus class, we discuss limits a little bit. And you'll learn about how to handle instances where there's 0 over 0, and there's instances where you need to deal with that with the difference quotient and everything. But if I let x be 4, the simplified version of this becomes 17 over 5. So make sure everything's cool there. Yeah. And 17 over 5 is approximately equal to 3.4. So I'm going to have a hole at 4, comma 3.4. And because the 3 halves stays, the 3 halves is still going to be an issue in this one down here, I could say that I have a vertical asymptote at x equals 3 halves. So we have these two. This one also had a hole and a vertical asymptote, and that's how we handled it. In the last one, go to pink. I have j of x, and let me make a little bit more room here. I have j of x equaling 2x cubed minus 4x squared over x squared minus 4x plus 4. So again, for this, tell me what the domain restrictions are for this. Well, if you go through and factor the top and bottom, because we want to factor the top to see if there's any potential cancellations, we factor the bottom to determine what my domain restrictions are. X squared minus 4x plus 4 is actually x minus 2 times x minus 2. I can write that as x minus 2 squared, but for the time being, I'm just going to write it like this. The top factors into 2x squared times x minus 2. So there is my factored form, more or less, of j of x. And I can see here I really only have one domain restriction. X cannot be equal to 2, because that's going to create 0 in the denominator. That's the only number that's going to make a 0 in the denominator. Well, I see that both of them have a multiplication of x minus 2 on the top and bottom. I mean, the bottom actually has 2 of them. So when I do my simplified form, now I only have one domain restriction. It has to be either a hole, also known as a removable discontinuity, or a vertical asymptote. Well, which one is it? Well, it's still the same rule. Yes, I canceled out an x minus 2, which is what creates 2 being an issue with this. The problem is, I still have x minus 2 down here. X minus 2 still means that 2 is an issue. And since after my cancellation, after I simplified, I still have the same issue, that means that it's going to be a vertical asymptote here. So there's only one feature that the domain restrictions cause here. It's going to be a vertical asymptote at x equals 2. And so that takes care of finding vertical asymptotes in holes. You're not guaranteed to have either, but you have to know how to search for them. The next feature that rational functions will have are horizontal or oblique asymptotes. And so let's take a look and see how we can determine those. So for this, in this course, you're gonna have to just get to know some rules to help you with the horizontal or oblique asymptotes. When when you get to Math 200, which you really should take before you take any calculus course, and again, you should be heading in that direction because you're taking this particular college algebra. Um, you'll eventually learn where these rules come from and why they exist. But for the time being, these are just rules you have to accept as they are. So what we do with this is that we look at the degrees of the two functions that make up the rational function. N is the degree of the numerator, M is the degree for the denominator. If the degree for the numerator is smaller than the degree for the denominator, then we have a horizontal asymptote at y equals 0. So there's really like no decision making there. I see a higher power of x. I mean, once I find my highest powers of x on top and bottom, if the highest power of x on top is smaller than the highest power of x on bottom, y equals 0 is the horizontal asymptote. All said and done. If they're equal to each other, if I find the highest power of x on top, find the highest power of x on the bottom, and see that they're the same degree, then what I do is I take a ratio of the leading coefficients. Again, I have to make sure I identify the leading coefficients correctly, because sometimes you might be given functions on the numerator and denominator that are not written in standard form. Please make sure you know the leading coefficient does not mean the first coefficient you see. It's the one attached to the highest power of x, and also make sure that you're aware of the signage of those. And lastly, if n is greater than m, then the function has an oblique asymptote found by finding the quotient of f of x. I'm going to say here minus the remainder. Basically, I carry through the division, and I carry it through until I reach the point where I would get my denominator, but I'm really only interested in what ends up in my, and it's going to typically be a long division in a lot of cases, but if you have a, if you just simply have a linear binomial with a leading coefficient of 1 in the denominator, you could use synthetic, but you know that doesn't happen as frequently as you would like. And even with that, there's things you know are losing with that. So sometimes it is better to do long division with these. So let's have a look at finding these structures here. Oh, by the way, an oblique asymptote simply means, you know, for our purposes in this course, slanted line. Oblique asymptotes can have many different shapes. They don't have to be linear. They could be other shapes. They could be parabolic. Um, I mean, there's a whole bunch of different shapes they could possibly have. For our purposes, they're only going to be slanted lines. So, you know, I'm going to have a vertical asymptote for sure, or a lot of cases. I'm either going to have a horizontal asymptote in these two cases, or I'm going to have an oblique asymptote in the case where the degree on top is higher than the degree on the bottom. Another thing I want to note before we get into actually doing the problems here is that these types of asymptotes, horizontal and oblique asymptotes, are end behaviors. What that means, just like any other asymptote, and asymptote is a term that you hopefully have heard before coming into this course and other algebra courses, but to kind of reacquaint us with that, and plus I mentioned it beforehand, an asymptote is basically, in many cases, a line that a graph approaches infinitely, gets infinitely close to, but never crosses. For horizontal and oblique asymptotes, that's not exactly as true. Um, as you go out like towards the ends, you go to negative infinity or positive infinity, yeah, that's the way it's going to behave. But when all the interesting stuff happens towards the middle of the graph, it is possible to have situations where a graph of a rational function may in fact cross through the horizontal or oblique asymptote. That's why if you have a horizontal asymptote, you could possibly have a range restriction, or you may not. You just have to see how it plays out. This happens more often when you have multiple, um, when you have situations with multiple vertical asymptotes, which can happen, and you might even get a couple of graphs in your homework in the suggested homework problems that may in fact have more than one, and you'll see some pretty bizarre behavior with that. Um, or situations like we had in D where we had a cancellation of the x minus 2, but yet it still remained there. Sometimes those kind of things cause situations where the graph might pass through the horizontal or oblique asymptote, but doesn't necessarily mean it's going to avoid it completely. It's only going to do so towards the ends. So let's look at the situations. I kind of gave away for D what's going to kind of happen with that one. Possibly. We got to be able to identify these asymptotes and then be able to use those as part of the graphing process. So let's have a look and see what kind of asymptotes we should expect to have. So for example 2, these first two. Now, it's for vertical asymptotes and holes, it's good to have these, factored. For the purposes of finding horizontal or oblique asymptotes, it's good to have them the way they are. Okay? That's not to say that if we go back and look at what we've done for the vertical asymptotes and holes and the work we did to identify those, sometimes using the simplified version is okay too. So I'm going to put that up here, simplified versions can still help. And we'll look into that and explain why momentarily. But ultimately you want to be able to look at the functions and say, okay, well, what's going on with, your highest powers of x and so forth. So for instance, in f of x, this is degree 0. I don't have any powers of x here. This is degree 0. The bottom is degree 1. So I have a situation where my numerator's degree is smaller than my denominator's degree. That's a pretty simplistic conclusion. I have a horizontal asymptote at y equals 0. If you think about it, in this particular function, since the top would remain 2, and the bottom, if I put bigger and bigger numbers in for x, I'm going to get bigger and bigger denominators. If I have a fraction where the numerator stays the same and the denominator just keeps getting bigger and bigger, the overall value of that fraction becomes closer and closer to 0. And that's what the asymptote is indicating. It means I'm getting really close to 0, but technically I'm never really going to touch it. I mean, I can have 2 over 3 trillion. That's going to be very close to 0, but it's not equal to 0. And the same thing if I pick really large negative numbers, I'm going to get a really large negative number in the denominator. The only thing that's going to be different is when I carry through that division, I'm going to have a really, really small decimal, but it's going to be negative. It's still getting closer to 0, but it's never going to actually equal it. So that's the reason why it ends up being that. It's pretty easy to see in this one. For the next one, it's the same issue. Up here, I have a degree 1 polynomial. Down here, I have degree 2. If you remember, we also said that the simplified version was 1 over x minus 3. If I look at the simplified version, it's the same thing. I have a 1 on top, and I have something on the bottom that could get really, really big if x is really, really big, which means I'm getting closer to 0. Or it could be really, really, really negative, but large value negative, which means in both cases, the fraction's approaching a value of 0. If I look at the original one, I can simply say, well, clearly, if I put a value in for x, the x squared is going to make it change into a much larger number. Um, so than just plugging in for x. So even if I plug like a million in for x on top, I plug a million in for x on the bottom, that's going to be a million squared. You're talking about, what's that going to be, like a trillion, billion? It's going to be much larger as a result. So I'm still going to have a situation where the bottom number is going to be much bigger than the top number. And as that keeps getting more and more of a discrepancy, the closer to zero I get. So much of the same way, B has a horizontal asymptote at y equals 0 as well. So again, in these two situations, because the degree of the polynomial that was the numerator is less than the degree of the polynomial of the denominator, I get y equals 0 as the horizontal asymptote. Moving on to C and D. In C and D, for C and D, h of x, I can see here the top is degree 2. The bottom's degree 2. I'm going to have a horizontal asymptote. The thing is, I had to come up with what that horizontal asymptote is going to be. Well, according to the rules we discussed before we got into this example, it's going to be a ratio of the leading coefficients. So since the x squared is the highest power of x on top, 4 is the leading coefficient. X squared is the highest degree on the bottom, so 2 is the leading coefficient. So this is going to be 4 over 2. So y equals 2 is the horizontal asymptote. Lastly, is degree 3. The bottom is degree 2. Once the power on top is larger than the highest power of x on the bottom, I know I'm going to have an oblique asymptote. Now what I have to do is going to be y equals, well, I have to come up with the formula for, in this case, it's going to be a line. Well, where is that going to come from? Well, what I do is simply carry out the division that I see. So, and since the bottom is in fact x squared minus 4x plus 4, I'm going to carry through that division with that. So I'm going to use long division. So I'm going to take the 2x cubed minus 4x squared plus 0x plus 0. Remember, I have to put any missing powers of x into it that aren't in them. And I'm dividing by x squared minus 4x plus 4. And I'm going to carry through the long division here. Now, I'm not going to stick, I'm not going to show the steps in slow motion and go through step by step. You should know how to do long division now. Just carry through the long division and see if you come up with the same thing as I do. I carry through the division all the way, even though I know that once I brought down the plus 0, whatever I would divide out, once I carry through the division, anything left would be the remainder. I really don't care about the remainder. I mean, 8x minus 16, I could eventually rewrite this as 2x plus 4 plus 8x minus 16 over x squared minus 4x plus 4. But it's really just this part right here that concerns me. That is going to be what the formula for the oblique asymptote is going to be. It's going to be the 2x plus 4, which of course would be a slanted line. It's in slope-intercept form, and you'd be able to graph that. So this is the information I have gathered so far. So far I have found any and all vertical asymptotes and holes. I have found whether or not it has horizontal or oblique asymptotes for each of these, and then discovered what it is. Now I'm ready to graph. So let's look at the graphs for these, and that's what example 3 is. So here we are at example 3, and as you will notice, as I start example 3, I just transferred the information that we had figured out and determined from examples 1 and 2 for these 4 functions. So we have this information here. For A, all I really have are the vertical asymptote and the horizontal asymptote equations. So, I mean, I'm going to graph them, but usually, when we graph them, if you're using a pencil, you should be like either writing it, drawing it like lightly, or sometimes we use dashed lines for the sort of purposes of this video and using this feature here. I'm going to use a highlighter essentially. So x equals -4 is right here, and y equals 0 is here. So those are my asymptotes, okay? They're not part of the graph, which is why we draw them dashed or lightly, or in this case, I'm using highlighters, because they help us determine the shape of the graph. They really are not part of the graph. So the information I have discovered from examples 1 and 2 for this, I don't have any coordinates for this. All I know is that the vertical line x equals -4 is a line that the graph will never cross. The horizontal line y equals 0 is a line that, as it goes on forever and ever, the graph will never cross, but it may cross somewhere else, I mean, towards the center. I got to get actual points for this. And so I am going to resort back to coming up with a table of values and plotting them. But at least now with the information that I have, I can be more selective about what that information is. Because most of the interesting features of the graph, any twists and turns and bends and things like that, are going to occur around the vertical asymptotes. And if there's more than one, then you have to account for that. But that's where most of the interesting things tend to occur. So I'm going to put the -4 here, indicate it's undefined here because it is a vertical asymptote. But I want to make sure I pick some points that are near the vertical asymptote and some points that are further away. So for instance, I might want to pick -5 and see what goes on with that function there. I maybe want to pick -3 and see what goes on there because those are pretty close. I can even get closer and use decimals as well, but whatever I put in, these are things I'm going to put in and eventually calculate. So I might want to make them easy at first, and if I see that I might need to put in some decimals, by all means I'll do that. I also see what's going on a little further away from it. So I'll maybe say, okay, I'll find a point at 0 and see what goes on there. And for this one here, maybe say, let's go to -7. So we have some points that we could possibly try out. So basically here, I'm going to find and plot 4 points, and that should hopefully give me a good enough picture of what's going on, and I can draw it fairly accurately. So if I plug -7 in, I'm going to have a -2/3. Now, depending on how you have your graph scaled, you may have to take some guesses with this. 2 over -5 plus 4 is going to give me a -2. 2 over -3 plus 4 is going to give me a +2. And 2 over 0 plus 4 is going to give me 1/2. So I'm going to plot those points. Maybe make this a little thicker. -7, -2/3, we'll say is about there. -5, -2, we'll say is about there. -3, 2 is about here. And 0, 1/2 is about here. So the graph overall would look like this. Now, if it looks like you're touching your asymptotes, that's okay. Just don't cross through them unless you see evidence to suggest you should. But generally, that's what the graph is going to look like. And I could even at this point, get rid of the marks here to make it a little bit more definitive. Because if you graph these on the calculator, 84s, if you have one of those, they're going to tend not to show the asymptotes. 83s may. I know there was some later versions of the operating system that learned to exclude them, but most 83 pluses would graph the vertical asymptote. So just be on the lookout for that. When I go to part B, Again, I have minimal information here. I mean, I do actually have one thing that acts as a point, but starting off, I have x equaling 3. Make it a little softer here. X equals 3 as a vertical asymptote. I have y equals 0 as a horizontal asymptote. And I have the point -3, -1/6 as a whole. So -3, -1/6 will say is about here-ish. And I am going to indicate it with an open circle. So unlike the previous one, I have something that's kind of like a point on the graph because that open circle should lie along the graph. But again, I don't have a whole lot as far as it helping me figure out what the shape looks like. So likewise before, I'm going to set up a table. And again, I'm going to center it around my vertical asymptote. So 3 is going to be kind of where I'm centering it. Of course, that's where y is undefined. And again, I want to pick a value that's maybe closer to 3. When it's a little further away, I always try to incorporate 0 because the zeros are easy to work with. And then maybe one that's slightly, that's close but bigger, and one that's maybe a little further away. And what I could do with these, now the easy part about this, I can plug them into the original and get the same numbers I'm going to get as if I plug it into the simplified version. So having the simplified version can make a little less work. Because this is going to be a -1/3. And if you plug it into either the g of x the way it originally was or the simplified version, you get the same thing. This is going to be a -1. This is going to be a +1. This is going to be a 1/3. So I'm going to plot these points. 0, -1/3, we'll say is about here. 2, -1's about here, is right there. 4, 1 is right here. And 6, 1/3 is about here. So my graph is going to look something like this. And again, I'm able to produce a pretty accurate picture without graphing everything, without having to plot a whole bunch of points. That's the whole gist of doing this. For C, again, I'm going to start with plotting my horizontal and vertical asymptotes as well as the whole. So x equals 3/2. This one I might go with dotted lines because the 3/2 means it's 1.5. So like x equals 3. So the vertical asymptote would be about here. Now remember, vertical asymptotes are lines that the graph will never cross. Y equals 2 would be here. This is a line where it could cross in the center, but not necessarily going to. Towards the ends, it definitely should start behaving like a regular asymptote. And of course, I have a point at 4, 3.4. So roughly about here. And that's a hole. So I gotta make sure that I draw it more as a hole. So right about here-ish. Again, in the end, I only have one thing that acts as a point. I don't know what the rest of the graph looks like. So I'm going to choose some points. Again, I'm going to let the vertical asymptote be the central feature because that's where it's undefined. So I'll pick a value that's I'll pick some values that are bigger. So we'll say maybe 2 because that's pretty close by, and one a little further away. So let's say 4. Well, we already know what happens at 4. I could actually use the hole up there as a point. So maybe say 5. Just have one more point. Up here I can have 1, I can have 0. That should give me an idea of what things look like. And I'm just going to put these values in. So 1, -5. I put that dash line in the wrong spot. I put it at 1/2 instead of -1/2. Easily corrected. So again, I have the 0, -1/3, which would be about here. I have 1, -5, which is right here. Which kind of shows me if I might want to pick a negative number to put in here, but generally the graph should just approach here. It'd probably be better for me to find another point it goes through, but that's pretty accurate. At 2, I'm going to be at 9. So 2, 9. I have this point here acting as a point at that hole at 5, 3. I have a point right here. So the graph should do something along the lines of this here. Again, I'm looking for, like when you do the graphing parts, I'm looking for some coordinates that you're calculating, some points that are accurately produced. If it's not perfect, that's okay. I just don't want you just like to like get a graphing region to say, okay, it just looks like, and you don't even really care where it goes. They have to be a little bit precise, okay? I'm not looking for perfection, but some degree of precision should be shown if you want to get credit for it. So it's a multiple choice item that you can pick the right graph. And lastly, for D. So we have the vertical asymptote, x equals 2. So x equals 2 is a good vertical asymptote. Nice light vertical asymptote. The oblique asymptote is y equals 2x plus 4. So I have to kind of imagine, going through my process of graphing. It might be not showing up as super well, but here's generally where the asymptote is for that. That's the oblique asymptote. And looking at this and the way I started it off, I'm not leaving a whole lot of room like up here. They're crossing. I mean, the two asymptotes are crossing there, so I may want to rescale this. So I'm going to pause for a second and rescale this, and then redraw it. So to show more of the graph, I decided to rescale this and go by 1s on the x-axis still, but go by 2s on the y-axis. So when I still plot x equals 2, it's still going to be here, and I'm going to use dashed lines this time. It's a little some more simplistic of graphing the line if I'm not using a thick marker. And y equals 2x plus 4. Now the careful thing is I have to remember first, plus 4 is here. That's going to just be 2 up. And I have to remember that as I go on these grids, one grid is 2 in the vertical direction, whereas left and right it's 1. So the slope of 2 is going to look like this on this particular graph the way it's been scaled. So you don't have to scale the x and y axes the same way. But at least now I have a little bit more room, like up here, you know, beyond the intersection of the two lines. I mean, that's an important area of the graph. I mean, I have to see what goes on around it. But I mean, I have 4 regions now. I want to be able to see if there's anything that goes on in this region up here. I want to be able to see it. Whereas before, it was kind of it was falling off the graph. I still use the vertical asymptote as a central point. That's where it's undefined. And so I want to pick a value some values that are close by, maybe one a little further away. Same thing here. And we'll just say, I always put 0 in there regardless. So, I mean, sometimes, 0 is not that far away from 2 either. So, but I'm just going to, so at 0, -2, if I put that in, I'm going to have 8 over -4, which is -2. At 0, I'm going to have 0. At 1, I'm going to have 2 over -1, which is -2. At 3, I'm going to have 18. At 5, I'm going to have a rather large number, 50 over 3. And 50 over 3 is about 16.7-ish. So I'm going to plot these points. So -2 is here, 0, 0 is here, and 1, -2 is here. So the graph is probably going to do something along the lines of this. And here I'm going to get closer and closer to that asymptote. Up here, I'm going to have at 318, which would be here. 5 will be at 16.7. So about here. So the graph's probably doing something along the lines of this. And that's what that graph would look like. So now with these being drawn now, I want you to come down here and answer the question I'm going to pose in Nearpod, or pose in PlayPosit. Match these graphs with now their appropriate examples. So label them A, B, C, and D. Well, if I zoom out, we can see the results that we end up with. So this one here, the first number 1 is clearly example C. 2 is clearly A. 3 is clearly D. And of course, 4 is B. And so those are the values we have for this. Now, let's put all of it together and have you do this all at once. So, as we go to this example here, and I'm going to zoom in a bit. Now, I'm not going to be able to check this up very well, on PlayPosit because it doesn't let me give you anything to graph and check on that. However, I want you to pause the video, try this problem, and then once you're done and you've produced a graph, see what you're able to, how close you are based on what I show. So take a moment, pause, and then come back and go through this. Now this one here is a little bit more challenging. It's, it has some things, that you have to do much like you had to do with the previous one. However, at the same token, there is some differences in this. It's kind of representing an interesting situation here. So, first what I'm going to do with this, and what you should have done with it, is that I'm going to factor the top. Well, the top doesn't really factor in anything, so it's going to say 2x cubed. The bottom is a difference of squares, so it ends up with x plus 2 and x minus 2. And it's important for me to have that because, now I can say like, well, I have domain restrictions. X cannot equal -2 and x cannot equal 2. So if I didn't realize that before from the x squared minus 4, which I could just simply set equal to 0 and solve that way and figure out what these are, I can at least see it now because once I have them factored, I can figure out what makes them 0. Well, as you can see here, there is no division that can be done. So, there's no cancellation it's going to have. So I don't have any holes. There's no holes on this one. But what I do have are 2 vertical asymptotes. So I have vertical asymptotes at both x equals -2 and x equals 2. I'm going to go to the graph and put those in a while. Again, it's going to help me figure out some things about the graph later, but right now that doesn't really give me anything on the graph. Now I'm going to look to figure out whether I have horizontal asymptotes or oblique asymptotes and find out what it is. I notice the degree is 3 on top. The degree, going back to the original one in particular, is degree 2. That means I have a higher degree on top than I do on bottom. That tells me I'm going to have an oblique asymptote at y equals, but I got to figure out what that is. So I'm going to go back to the original 2 numerators and denominators because I really can't do any cancellation. I can't come up with a simplified version. So I'm just going to take the 2x cubed, remembering to represent all the other powers of x. and divide it by the x squared minus 4. Again, remembering to represent any of the missing powers of x I'm not seeing. And I'm going to carry through the long division, so the quotient will eventually be what y equals for the oblique asymptote. So again, I'm going to carry through the division. I'm not going to go step by step because you should know the procedure by now, but you should be able to check your work once I'm done with this. So I get to this point here. I mean the now what I have left has a degree that's lower than what I'm dividing by. So, technically I would have this plus 8x over x squared minus 4, but that means that this is the quotient. So y equals 2x is what I'm going to be graphing here. I think I can leave the y um, grid going by ones, so I'm just going to plot y equals 2x. And so there is my oblique asymptote. Now again, these are just features that the graph is going to avoid in some way. May cross over, may not cross over, but towards the ends of the oblique one should avoid, and certainly the vertical ones will be avoided all the time. This doesn't let me know what's on it. So here's what I need to do. Now, when I have multiple vertical asymptotes, if I'm going to have any situation where my graph crosses my oblique asymptote, it'll probably be occurring between the two asymptotes or pretty darn close to them, um, so in between the asymptotes, I might want to pick some more points is what I'm getting at, not just say, okay, one close, one far away, when I start mapping out my coordinates I might want to plot here. I want to include the -2 and the 2 for sure. I mean, I'm going to indicate them on my little chart here because those are central features of the graph. For the time being, I think -1, 0, and 1 would be good in between. I mean, I could put in some fractions if I want to, but it's not necessary. Make sure I have some that are close by here. Maybe go a little further out and even yet a little further out. And same thing here. So I would want to compute all of these. Now I'm going to go through and compute all these. I'm going to do it in fast motion, but basically each one of these x's I've just chosen, based off of what I have and what I need and where my vertical asymptotes are. I'm just going to plug these in and, get the y values by plugging them into f of x. So if you give me a moment, I'm going to do that and write them in. So these are the values that I computed by plugging them in. Some of these don't fit on the graph very well. I mean, because I only go up to values of 10. So let me just do a quick rescale of my graph. I'm instead going to let my y-axis go by 2s. So I'm just going to do a quick changeover. So it's a slope of 1 on this graph, but I have to remember and vertically each grid mark I'm moving is 2. And changing your graph around as you do this and thinking about your scaling are things that you want to do. You want to be maybe in constant flux until you get something that you can fit the entire picture on. Because I want to be able to put some points on here, and a lot of my points, especially on the left and right of the um, two vertical asymptotes, the far left and far right, I was losing points. I mean, there wasn't anything I could do with them. Um, so let's plot these points now, and I'm going to again fast motion this part. So there's approximately where the points would go. But knowing about what the graph's doing, I would expect the graph to do something like this. They make it a little thicker so we can see it a little better. Here, the graph is passing through my oblique asymptote, but I'm going to expect it to do something along the lines of this. And again, if I can verify this by picking some additional points on this. And up here, I expect to do something along the lines of this. If I get this directly right. And that's what the graph would look like. So I can make some pretty good predictive behaviors with very few points based off of me knowing how things obey vertical asymptotes and things like that. I don't have to get worried about this point right here where it crosses, the oblique asymptote in the middle, because I kind of expect that to happen since that's towards the middle, but towards the ends it starts avoiding the oblique asymptote as it should. And so that's a kind of interesting things that can happen when you have multiple vertical asymptotes. Also, when there's chances for or things cancel, but yet you're still left with the vertical asymptotes, things like that can sometimes happen as well. Didn't happen with one example we did, but it can happen. So be on the lookout for those things. And sometimes you might have to pay a little bit more attention and graph a little bit more detail and pick some more X and Y values. Means it's always a good idea to throw this up on your calculator, see what it looks like. And if you're seeing a feature that looks like it's totally different to what you're graphing, you may want to explore into that until you get the hang of knowing what to expect and what to show. But that brings us to the end of this video. If you have any additional questions with this topic, please make sure to bring them up in class or come and see me during my office hours. Until I see you in one of those situations, or until the next video, I will see you around, and have a good day.